Hey, I want you to be mine. What's up, guys? This is Physics 2212 Lab 4, Magnetic Field of a Bar Magnet. My name is Ben Hubby, and let's get right into this thing because we got no time. In this lab, we will examine how the magnetic field of a bar magnet changes with distance. Our goal is to compare the observed magnetic field to the predicted values for both on-axis and off-axis positions. We'll be using VPython to do so. Some assumptions. There are no other magnetic fields interacting with the phone besides the bar magnet and the Earth. The bar magnet acts as a magnetic dipole. The magnetometer is perfectly aligned with Earth's north-south axis. The magnetic field falls off as distance increases, which is kind of obvious, okay? And we know where the magnetometer chip is in the phone. You know what? A little hint, we don't, but we're assuming we do. Here are the results. Biot-Savart's law. The Biot-Savart's law describes the magnetic field generated by a steady-state electric current, stating that this field at a point is proportional to the current element and inversely proportional to the square of the distance from the element. Right here, that is Biot-Savart's law. Magnetic field of a dipole. Magnetic field of a dipole is the field produced by magnetic dipoles such as a small current loop or a bar magnet, which is what we're using, characterized by a strong field near the dipole and a weaker inverse cube dependence on distance in the far field region. Right here, excuse me. Okay, and the distance dependence formula basically just saying that as distance increases, magnetic field decreases. Two boys, these will be very crucial for later. Okay. Experiment procedure. Adjust the phone's orientation so that the magnetometer is perpendicular to the Earth's magnetic field, aka the x component will be 0. Identify the exact location of the magnetometer chip within the phone. To do that, we will be orientating it, and we will be finding that little chip right there. Very useful. Then we will measure the distance between the magnetometer for both on-axis and off-axis positions. Experiment setup. We have the bar magnet, as you can see right here, with the smartphone, with the magnetometer sensor that we're assuming is right there. The meter stick, we got one right here, and later we'll put another one up right there. Magnetometer app is displayed, and some tape is useful. Experiment on axis. Our data collected and displayed. Here we try to get as close to 0 as possible. We got pretty damn close, but we weren't perfect. That'll come into later. We got two numbers for this perfect line of best fit. Very important. This is n. Okay, this is our n value. You can see it right there. Then this is our natural log k. Now that's not the same thing as this, is it? But guess what? With some experimental calculations, it'll become that. Okay. Use natural log k is negative 14.824. K becomes this, therefore. Okay, and then we have, with all that useful stuff, we throw it in the equations, and the magnetic dipole moment becomes 1.8235. Okay, pretty dang good stuff. We also did this for off-axis. As you can see, we then moved it up on this ruler. Okay, off-axis, and we got these values, which will become crucial into later when we're comparing stuff. Okay. Okay, and here was we'll be using this in our computational model. Boom! Computational model. Here's our magnetic dipole moment code that I created for this computational model. Okay, here is my scaling, here's the distance, and here is that d-perpendicular, which you saw right there. And this, my friends, this is our outcome. Okay, here's the magnetic magnitude of B at 45 degrees, 1.663. Now, is that what we got here? No. No, it's not. We were actually really far off. Okay, we tried. We did our best. This is what we got here. As you can see, not really. Okay, you know what? We weren't perfect, but we tried, and that's all that counts. Because guess what? We know why we failed. Other magnetic fields were definitely present. Okay, my teammates were playing with magnets. I told them to stop, but they didn't, and that is what caused error. The exact location of the magnetometer is not found. There were errors when measuring visually with these millimeters. We were probably off by a couple millimeters here and there. And accidentally bumping the phone did not help. Also, we failed to perfectly line up with the north at the beginning, and when we failed to that, we also probably bumped it here and there, meaning that there is data. Our data is skewed. Okay. Now, what if you hadn't oriented your experiment to compensate for the magnetic north? Well, how would that affect the results? If the mirror stick were placed at an intermediate angle, the Earth's magnetic field would interact with the bar magnet's field unevenly, leading to inconsistent measurements. Boom! Now, if you were to stick two identical magnets together end to end and run the experiment again, how would that affect the data? With two identical magnets placed end to end, the total magnetic field strength would increase. And it actually double. But, excuse me, since the magnets are aligned in the same direction, the overall field orientation would remain unchanged. That is our what if, that is our answers. I hope you guys enjoyed this lab, because I'm going to see you again with some time, okay? Thank you for listening. I hope you learned something new. I want you to be mine again, baby.